Hello, my name is Shivdath, and today we're going to discuss a very important and interesting scientific problem called the percolation problem. We're going to look at a kind of a specific case of it, but without further ado, let me define what the problem is. So imagine you have an n by n square grid, an n by n array, if you will. So each one of these squares, let's call it a site, and the idea is that we put a layer of, and all of these sites are closed, and we put a layer of water at the top. Right? So when all the sites are closed, water can't, seep through. But water can, if the sites were open, right, water can move down, it can move left and right. It can't move up. We don't care about it moving up, because if it's moved to a square, it has to have basically water can move down, left and right, but only through open sites. So the question is, if we have all these sites closed, right, and we put a layer of water at the top, and we randomly start opening sites from here. In other words, they're closed, we kind of remove the blockage. What percentage of the sites would we have to remove, would we have to open, for water to be able to percolate from the top to the bottom? In other words, for a single drop of water or a square of water to be able to reach the bottom. And now, it may seem like the answer would, first response may be, wouldn't the answer depend on the size of the array and which squares were randomly opened? Like, what if I randomly opened 1, 2, 3, 4? That's it. I needed 4 squares and I got all the way to the bottom, but water would flow straight down. But in another example, I may open this, then I may open this, then I may open this, then I open this, so water's come here so far, and then I open this, water comes here, and then I open this, water comes here, and then I open this, nothing happens, and then I open this and water comes here and finally percolates. In other words, 1, 2, 3, 4, 5, 6, 7, 8, twice as many sites were open in this case. So what we're really interested in is, as the size of the grid, as n, this is an n by n grid, n squares on each side, as n tends to infinity, as n gets really large, is there a certain percentage, or do we see any pattern? And it turns out amazingly that there's a really sharp threshold. In other words, as the size n tends to infinity, the fraction of these sites that have to be opened randomly for water to be able to percolate to the bottom is 0.5927, let me get this right, 46. It's amazing that we see such a sharp threshold. In other words, if you open less than that number of the sites, water won't percolate. And the moment you kind of get beyond that threshold, water will immediately percolate. It's like this really sharp threshold. So if you were to plot a graph of, whether water reaches the bottom or not, and this is the fraction opened. What you really see is that when this fraction equals to this critical number, this critical threshold, 0.59274, before that, water won't percolate. And after that, water will percolate. And kind of, there's a sharp jump there between not percolating, suddenly it percolates the moment you hit that frequency. So this is the percolation problem. This was this was really a two-dimensional example, a two-dimensional square example. Notice that you can try the problem for rectangles as well, and various thresholds have been developed for different shapes and sizes. They've been thresholds developed for triangles, triangular-shaped objects. There's been thresholds defined for 3 dimensions, so on, n dimensions in fact. But usually there almost always exists a threshold. But one of really the most fascinating parts about this problem is that There are many examples, such as this square example, for which there's no known yet mathematical solution. In other words, there's no known mathematical reasoning that will get you to this ratio, that proves that when this fraction of the sites are randomly opened, that water will percolate to the bottom. No combinatorial proof, no no algebraic structural manipulation, nothing. But using computer science and numerical simulation, we're able to kind of get with an amazing amount of confidence the sharp threshold. So this is a great example of where computer science can come to the aid of scientific understanding even when math fails. Math couldn't get to that solution, but just by simulating the results on a computer, even though we don't have a proof per se, there's no hardcore evidence. Like there could be a malicious being just playing a trick on us and making it so that we've just been terribly lucky every time we got this ratio so far. But leaving those speculations aside, it's amazing how computer science can enter a problem which is kind of intractable mathematically, and something that nobody's been able to get a closed form solution mathematically so far. I hope you enjoyed it. It has tremendous amount of applications in various different fields. A great example is in material science, where you're looking at electrical conductivity, and you can look at a square of water as an electron, and this grid as a metal or whatever material they're looking at, and open sites are paths through which, or kind of places that the electrons can move through, while closed sites are perhaps insulators where the electrons can't move, which don't conduct. And you want to see what fraction of that material do you have to make conducting for electricity or electrons to pass from one end to the other. That's one great example. And I hope you enjoyed it. Thank you very much.